Now the coupling is usually D is equal to epsilon E, J is equal to sigma E, and B is equal to mu H. So these relate the field quantities to each other in different media. Sigma is really the conductivity, so if there is a media that allows conduction current to flow, sigma can have a bearing on the effects. Mu is the magnetic permeability. If you have magnetic materials, mu itself becomes very important, mu relative especially. Generally speaking, dielectric materials, you only worry about D is equal to epsilon E, J itself goes away, and usually mu is just mu naught. Now, when we talk about lossy dielectrics, I want to make it a point. I really want to make this point so that there's no problem. Remember, when we talk about a dielectric, we're talking about stuff that has molecules that have plus and minus charge centers, and they get stretched. Basically, there's like a spring in these things, and if you apply an electric field in this direction, then it elongates them. They tend to get like this, the spring stretches. I'm just trying to give you some sort of a mental picture of what goes on. Those things are stretched this way. You'll find it's not elongated very much. And when they stretch, they store energy. And then when the field reverses itself, they contract, and then they stretch the other direction. Now, in the process of these dielectric molecules being stretched by the electric field ever so slightly, there's also frictional losses involved. I hope you can appreciate this. Just imagine anything that you're moving, pushing it together, pulling, pushing. As fast as you go, you're generating some sort of heat. You have to. There's going to be frictional heat in there. Some sort of heating will occur. It's a lost term. Now, the difference between what I'm trying to show you here, when you have dielectric motion that gives rise to dielectric current, is there's no real sigma in here. There is no little, you could paint electrons. You can't watch that thing go through the lattice at all. Everything's, all the charges are bound. They're just being pulled a little bit and then pushed a little bit in the other direction. Small displacements. But there is a loss. And the way that mathematically engineers describe this in terms of something that's useful for design is with what's called a lossy dielectric or complex dielectric. So what they do is use this right here. We're assuming sigma 0 for now. That's not in Whitmore's book. And we'll just use B is equal to mu 0H. So it's going to be a non-magnetic material. Here's where the assumptions start. These two cases. And when we have this case, now we use epsilon complex. And that's equal to some epsilon prime minus J epsilon double prime. This is going to bother you a little bit. You're going to say, now going to the frequency domain, I didn't say that explicitly yet. But the minus J epsilon double prime accounts for the lossiness. And you'll see this now the way I do it. So I'm going to go to the frequency domain. My first one is going to be curl of H. We're assuming sigma 0 will be equal to J omega epsilon complex E. And that's equal to J omega epsilon prime minus J epsilon double prime times E. Okay. Now make a note of this. Epsilon prime is just equal to epsilon relative epsilon naught. That's the old epsilon relative epsilon naught that would be there if you were at 0 hertz, if there was no frequency variation. Y'all follow me on that? This second term, epsilon double prime, has to do with dielectric losses. I'm going to go over here. I'm going to keep talking about this in a way I hope that will really show you why this is important. If you go here and you take the next step, that means curl of H is equal to Well, you're going to have j omega times j is, well, times minus j. J times j is minus 1 times the minus is plus. So I get omega epsilon double prime E right here. And then I get plus j omega epsilon prime E. Now, here's where I try to really make sure you see this. Back here, if you took just this equation and went to the frequency domain, you would have this. I mean, I'm going to go to the frequency domain, and then I'm going to show you what you would have sigma E plus j omega epsilon E. You all follow me on this? I'm going to the frequency domain, and I'm going to replace j by sigma E. I know I said sigma 0 in velocity dielectrics. That's true, but I'm trying to build a case of how come that's a loss mechanism. You see how the coefficient of E by itself is sigma, and that accounts for the conduction losses there. You all see this, class? All right, look over here. This term is like sigma, only now we're not talking about a sigma that allows electrons to flow in a continual fashion through the lattice. This is a loss term that has to do with bound charges and the loss involved at different frequencies. And by the way, one thing that's very important to see is this loss is proportional to frequency, and that's absolutely true. And here's why. For a given electric field strength, every time you go through a cycle and you flip the polarity, those molecules, they contract and then they are compressed in a sense, then stretched back out apart. You all follow me? If they're aligned. That causes a frictional heating. The amount of frictional heating that occurs is proportional to the number of times that happens, and that means it's proportional to frequency. Higher the frequency, more times it happens per second. Does this make sense, everyone? And this is a general rule. So this is the way we deal with dielectric losses right here. So a bit more information. You have to get an appreciation for this. Well, with materials, how do the material science characterize materials and then present them? Usually what they do is they call something a loss tangent. So what they'll do is they'll take a look at these two currents, and this is the loss current, or it's the real part of curl of H, and this is the imaginary portion of the current, or it is really the displacement current density. So they'll plot this, and I'll do it here. They'll have a plot of the real arc of curl of H here, and then they'll have the imaginary part of curl of H here. Well, the real part of curl of H is just omega epsilon double prime E, and the imaginary part of curl of H is going to be just omega epsilon prime times E. Now, can you all follow me? I'm trying to show you this. We've got a plot here. I'm taking the imaginary part on that, the real part on this, and that means there's going to be some line that's got a linear slope where this would be the maximum extent of the two. Now, what you can almost see happening is there's omega and E in both of these, right? You all follow me on this, class? So they just...
Is the epsilon on the imaginary axis E double prime?
No. Single. My bad. Y'all with me on this? All right. You can get rid, in Whitmer's book he doesn't do it, but you can get rid of omega and E. And really on this axis what you have is just epsilon prime, or double prime, versus epsilon prime. You can just, get rid of these things. I know he starts this way, but really the only thing you want to think about is epsilon primes on that axis, epsilon primes on this axis, and epsilon double primes on that axis. Y'all follow me? And let me give you a picture of the book where this is, in case you want to look at it. Page 333. And Whitworth includes sigma in this picture. Sigma just clutters the picture. Sigma is real current. I mean, sigma has to do with real conduction current. But in this picture, here's the thing to know. This angle right here is delta. And if you look at this, well, the height of this thing is proportional to epsilon prime. This dimension is epsilon double prime, so you can see, and this is the important part, if I take the tangent of that angle, that's opposite or epsilon double prime over epsilon prime. And this is called the loss tangent. Now, the only thing it does is when you have material science information and you're doing designs, here's the deal. Any dielectric that's worth using is going to have some loss. It's just the reality. But you want to make sure at a given frequency that this number is very small. This ratio is very small. Think about epsilon double prime proportional loss, epsilon prime proportional to energy storage. That's a better way to think of it. So we would ideally like this to be zero, but it's never zero for any real material. There's always some loss. And this epsilon prime and epsilon double prime are functions of frequency, strong functions of frequency. Please remember this. So if you're ever involved in looking at materials, that you want low loss materials, and the best example of this is, do you know what any type of coplanar circuit board is, or FR4 board, or anything like that? We have a copper clad and a dielectric and copper backed, right? And you mount components and then etch off the copper you don't want, and you have circuitry. Do y'all follow me on this? It's like lithography for VLSI technology. Well, the material in between the upper and lower copper pieces is a dielectric. You can get really expensive materials that are very low loss. They're called duroid board. They're about $100 a square foot. Or you can get much cheaper stuff for lower frequencies, basically mounting components and stuff like this. Do you know what FR4 board is, that green board? Y'all know what I'm talking about? Some of you do. All right. The costs vary orders and orders of magnitude for these materials. And the thing is, the lower the loss, the more expensive the material. Most of the time, they're not worrying about storing a lot of energy between these two. What they're worried about, what they're concerned about is they want an epsilon relative that's greater than 2, 2.5, and they want something with very low loss at the frequencies of operation. And that's really what the loss tangent tells you. Now, in his book, I'm used to seeing this where we have tables and tables of given frequencies, but in his book, I'm just going to give you a reference to some. On page 625, he has material properties. He just shows at 1 megahertz the values of the loss tan for a bunch of different materials, including mica and ice and quartz and he's got even water in there and seawater. But in the real world, when you're dealing with kind of these materials and you're dealing with lossy materials, you would like to see an example of a real problem. And I can give you one later where you're designing a capacitor and you've got to select materials to create this capacitor. It's going to be a conformal capacitor. It's part of a circuit, an overall circuit. But this is the real thing that you have to deal with. So obviously, epsilon prime, double prime, is simply equal to epsilon prime times the tangent of that angle. And the truth is this: what do you know about tangent of very small angles? Tangent of x is about x if x is small, right? Do you all remember that? Same as sine of x is about x if x is small. That has to be in radians, by the way. So if you're talking about something with a loss tan here, or the tangent, that angle right there, is something like less than a degree, then you don't even have to take the tan. You can just put the angle in radians there times epsilon prime. But usually what they give you is the tangent in the tables. I'm just going to tell you that. And this will vary a great deal. This value for the loss tangent of that will vary a great deal versus frequency. The loss tan at 1 megahertz may be very low, but the loss tan at 1 gigahertz may be very large for the same material. So please just remember that. It varies wildly. And I'm just trying to give you some insight in this. Okay. So that's really, in a nutshell, how you deal with lossy dielectric materials in terms of its basic understanding. And I can tell you this, like, the problems in his book about this are trivial. I mean, that's, yeah.
So just one thing, so for epsilon double prime, will units still be in ferrets?
With what?
Will units still be in ferrets per meter?
Well, they have to be the same units.
Is it just, will epsilon double prime be given coefficient values to like an epsilon relative, and you multiply that by epsilon known?
Well, let me back up here. The units of epsilon prime are J times epsilon single prime, double prime. So this unit would be farads per meter, but with a J complex. That's the only thing. But I really wouldn't worry about that. The units they work out. They have to, just remember this, that like, when I have this right here, whatever the units are for this, they have to be the units of this. So J times farads per meter have to be the same as farads per meter. Yeah, that would be right. Anyway, next I want to get to conduction current and something called skin depth. How many have heard of skin depth? One, two. This is a real important concept for engineers to appreciate. Now, I've gone through good conductors in terms of the general form. I'm going to put down some information about this. So, now this is going to be good conductors. All right, examples of good conductors. I should have probably gave you a few examples of lossy dielectrics. Can think of, just from you guys, what's a good conductor to you?
Copper.
Copper's probably, copper,
Gold.
yeah, gold. How about silver? Silver's probably the best of these, right, in terms of its conductivity at room temperature. You can go down to less steel, right? Steel's a good one. Aluminum's pretty good. And what you're looking at is the value of sigma. Here, the value of sigma is greater than about 10 to the 6, 1 over ohm meters. That's a good conductor. Generally speaking, good conductors to you and me mean metals, generally. However, they can mean things like it can be, when you think about carbon nanotubes that are doped, those can be great conductors. When you think about just carbon or graphite in certain, if it's processed a certain way, those are good conductors. Generally speaking, you think about things that have a conductivity of greater than 10 to the 6, but that's not necessarily true. What it really means is when sigma is much, much greater than omega epsilon. That's the general, and here I'm not including the loss term for the dielectric, just epsilon, relative epsilon naught. When this is true, you've got a good conductor. That's the general form. And when you look at good conductors, those are the examples I like to use. And you take a look at material parameters. First, when you look at the propagation constant, it's alpha plus J beta. If it's a good conductor, it's square root of J omega mu times sigma plus J omega epsilon. But because it's a good conductor, we can get rid of this term. And we just say this is equal to square root of J times omega mu sigma. And that's really 1 plus J times the square root of pi f mu sigma. Now I'm going to stop for a second and let you just take a look at what I wrote. I went through this a few times. How many remember me going through this? Okay. Then I'm making a few points. First is that's the general form for the propagation constant, for gamma. When you have a good conductor, sigma is so much greater than omega epsilon, you can ignore the omega epsilon with the J. So that means you end up with this, right? Can you all see this okay? Well, square root of J we talked about is what? It's really 1 plus J over the square root of 2. Do you all remember that, class? If you break that out, then you get square root of 2, omega over square root of 2, which is just, since omega is 2 pi f, it's just pi f mu sigma. You all follow me? And that means one thing that's very important. For a good conductor, you will have alpha equal to beta, and that's equal to the square root of pi f mu sigma. So skin depth it applies to a given frequency. It obviously does not have some general meaning for all time, but it has to do with the frequency. And when you look at what happens now in a good conductor with propagation, you find the E field in the phasor domain, we'll say it's EX. The E field itself would have some E0, e to the minus alpha z, e to the minus j beta z, and I'll call it in the AX direction. Now this is just a propagating wave going in the positive z direction. I want to try to keep this simple. Y'all remember how Wentworth always uses the z direction for propagation and orients the E field in the X direction, just for simplicity, right? He's talking about a plane wave propagation. So if you were to plot versus z, the magnitude of the E field here, you can forget about this e to the minus j beta z. That's a phase term, right? It's like e to the j minus j 20 degrees, 50 degrees, 70 degrees, always has a magnitude of 1. Do y'all follow me? So forget that, you're plotting this. What you're seeing is this happening. But now this magnitude is simply E naught, the initial magnitude, and it's e to the minus alpha z as the wave propagates. It's propagating in that direction, so this is really the envelope of the magnitude of the E field. And you can see as it propagates, it decays in magnitude. It's not mysterious here yet. But here's something that we use all the time. We say the point where you have the E field being equal to E naught e to the minus 1. At this point, this is given the symbol, unfortunately, the same symbol as the lost hand, gamma, and this is called the skin depth. Now, if you look at this, since I have e to the minus alpha z here times E naught equal to E naught times e to the minus 1, you can see that really alpha times z is equal to 1, and z will be the skin depth, which is 1 over alpha. Just take a look at that for a second so you can appreciate it. So really, what they're finding out is this skin depth is nothing more than the distance where all of a sudden the field strength drops to e to the minus 1, its peak. Well, this is about 33% of its maximum value. So it's dropped 66%, roughly 67% of its peak value. But that's a very important point, and here's why it's an important point in a second. This is called the skin depth, and it should make relative sense to you. It's a measure, a metric for how fast something attenuates, or how much distance the wave can be expected to move through before it's significantly attenuated in any material. Now, some of you probably remember these type of rules of thumbs, but if you're 5 skin depths in, you basically have a signal that's gone. And that should make sense to you, because you remember when you were, I forgot if you got this in your statistics course or what, they talk about the standard deviation, right? If you're within 1 standard deviation, you're 90%, 2 standard deviations, I forgot it was 95. Anyway, it keeps going on this. Well, with the rule of thumb with skin depths, if you're 5 skin depths into a material, the signal is considered gone. It's, I mean, by any measure. All right, there is something there, but it's such a minimal signal strength you don't have to worry about. So, how is this term skin depth useful to engineers? And here's the big thing. Now, there's proofs, and you can actually prove what I'm going to do in a. I may do it. a much more involved way, but it really doesn't shine light on what it's useful for. And again, this is something that has to do with the material you're propagating through. And the skin depth, like the lost end, is a metric use. It's some figure of merit for the material. But this is for good conductors. So, here's the biggie with skin depth. And it's AC, or high frequency resistance. I'm trying to teach this in a way that I would want it taught to me if I was sitting where you were. And I want to just go through a bunch of abstract math. So if you think about a resistor, let's do the simplest possible resistor. I'm going to take a constant cross-section resistor of a given length. And this has some sigma in it. And it's going to have a radius A. And it's going to have a length L. And I'm going to go ahead and do this too. I'm going to put a battery here, complete my circuit, assume the ends are metallized. And I'm going to drive a current through here. That's a DC current. Well, I know for this case, if the cross-section is constant, I know the area here, the cross-sectional area A, would be equal to pi A squared in meters, right? Meter squared. And I know the resistance of this material, and this would be the DC resistance, would be L over sigma A, or it would be L over sigma pi A squared. Y'all follow me on that? That's just standard resistance, right? Constant cross-section. You've seen it before. Now, if you take this same thing, but now I'm not using a battery anymore. I'm using something that varies as a sinusoid. So let's just say it's V naught, some V naught cosine of omega naught t. In other words, it's time varying voltage. Now the problem takes on a new dimension. Here's what goes on. When you're driving this, current is going to want to flow from this end to this end. And it's going to flow down the path of least resistance. Now, as it flows, what will happen is this. It'll hug the surface, and when you get that time-varying effect, it'll cause a wave to propagate towards the center of the wire. I know this is on dimensions that is really hard to appreciate, but I'm trying to blow that wire's cross-section up. Now, how far into the wire it goes is dependent on the skin depth at that frequency. So, next thing we do is something we're going to get the resistance, but now it's going to be resistance, and I'll call it AC resistance. It's still going to be proportional to length, inversely proportional to sigma, but now here's where the area changes. The current will flow. It'll basically be trapped in one skin depth of the surface, all the current. Now you can prove this, you can actually write the equation and then integrate out the current density through the entire cross-section of the wire, and it comes down to this value. So this is not something, it's not an approximation. So when you look at this, now when we look at the cross-section of the wire, that the current's gonna actually flow, and I want you to see this. Before, I used the entire cross-section of pi A squared, but now I want this cross-section of the wire, and this is simply one skin depth thick. Y'all follow me? Same value of sigma. Can you all see this, class? Now all the current is going to hug the surface of the wire. So what is this area? Well, the AC area here would be equal to pi A squared, right? That's the whole area, but then I'd have to subtract out the inner area. So it's minus pi times A minus the skin depth squared. So that's going to be pi, right? And then I have quantity A squared minus A minus delta squared, and that's going to be pi, and then you get A squared minus A squared plus 2A delta, and then minus delta squared. I'm just expanding this. Y'all follow me? I'm just giving the area here. With me, guys? Something I should say also. The only time you need to do this is if the skin depth itself is less than A. If the skin depth is larger than A, you can revert to the DC resistance. Y'all follow me? Because then there's no attenuation, no significant attenuation of the signal. But if the skin depth becomes less than A, less than the actual radius, then you have to do this. And here's the thing, usually for this one, I'm getting the area now, A squared minus A squared gets rid of that. So you get 2 pi A delta, and then you get minus pi delta squared. And here's where I have to make a statement. Usually, A, for this to work, A has to be greater than the skin depth in delta. It's usually much, much greater. As a matter of fact, in most cases, in almost all cases, you find that A is much, much greater than the skin depth when we're talking about skin depth variations of resistance. And that means, therefore, this area becomes approximately just 2 pi A skin depth. And let me make this a little more apparent so you don't have to worry about formulas all the time. Think of it this way. If you have this geometry, if you cut it right here, and then you simply stretched it out and laid it flat, it would look like something that had the actual circumference and length, which would be 2 pi A, and would have a thickness of the skin depth. Do y'all follow me on this, class? Just take this right here, cut it right there, and then straighten it out. Well, what's the area there? It's 2 pi A times the skin depth. And that's the best way to keep that in the back of your mind, to see it. Just assume everything flows near the surface of the wire, and let the thing go down one skin depth, break it, and spread it out like this. So that means this is really going to be divided by 2 pi A times the skin depth. And therefore, you can look at the ratio of RAC over RDC, and you can see for AC resistance, I have L over sigma times pi A squared. I'm sorry, that goes on the bottom. L over pi, or sigma pi A squared. And then on top, it's L over sigma times 2 pi A times the skin depth. The L and sigmas go away, the pi's go away, and therefore I get A squared on top divided by 2 A sigma, or it's really A that's right, A over 2 times the skin depth. I'm going to show you, I'm doing that for a reason. Because you see one thing, the ratio of the AC to DC resistance. As the skin depth gets smaller and smaller, it gets closer and closer to infinity. That's the only reason I did that last part. And I'm just trying to show you that the way, really, this is a single wire, it's a solid wire. All the current hugs the surface. Now here's the second part to this skin depth business that's important. I need to put this right here. How many have seen this before? I'm just curious. You've seen it in what class?
A little bit in Power. I did a lot of looking through Wikipedia pages.
Okay. was this in any of your power classes or not? Gross covered? Skin depth is very important for a lot of things. In power, for the earth and stuff, if you have a very conducting soil, it's much different in terms of the skin depth of that versus a very dry soil. And when they deal with something called grounding rods, the calculations change a great deal. Did Gross go through grounding rods at all? Anything like that? No. All right, so what's a problem that would be related to some of the stuff we just talked about? And here's a good one. Suppose I have a metal cable, and I've got an inner conductor of radius A, solid. And then I have an outer conductor. That doesn't look very good. Let me try to make that a little more symmetrical. Inner conductor of radius A, and an outer conductor here of radius B. This is a solid wire, but this is a thick sheath here. And I got a radius C. So this has got some thickness to it, and that would be C minus B. Are you all with me? And that's solid. And this is the cross section of a very long transmission line. Just assume you got a very long wire, or whatever you want to call it, conductor. You got an inner core like a standard coax cable. Then I got an outer sheath here that's got thickness. And you want to know the resistance per meter of this, the differential resistance. So if you think about this kind of a setup, you get, it's like a coax cable, right? Where you're going to have current flowing one way down and then returning this way, right? A differential mode. And you want the resistance per meter. So you need the resistance of the inner core and the resistance of the outer surface as well. Y'all follow me? Now here's the thing that's important. When you have a coax cable like this, even though this has some thickness, and you drive it with a signal, any kind of voltage, time varying voltage signal, I'll ground that, and I'll also take it connected here. We'll assume this thing's long. The actual electric field will be set up so it'll actually hug the surface of the inner wire, so you'll go one skin depth into that surface. And on the outer wire, it will hug the inside of the outer wire. That's always true. So if you take a look at this, if this thing was a high frequency kind of effect, you would get current flowing one skin depth there and then one skin depth here, but it would be on the inner portion. The real reason is because all the charges, the variational charge that's developed, will always be on the surface between the two conductors, never on the outer surface. Y'all follow me on that? So if you're calculating the resistance per meter of this problem, first you got to do one calculation. First thing, you calculate the skin depth, which is 1 over square root of pi f mu sigma. Did I put that down or not?
I put 1 over alpha.
All right, 1 over alpha, this is alpha is this. So this is the definition of skin depth right here. This is the big one. That's the one you need to remember. So now you go like this. If the skin depth is much less than A, let's assume it is, and we want the AC resistance per meter of this setup, you would find RAC would be equal to the resistance per meter of the inner one. That's pretty straightforward. So we're assuming the length is 1 if it's resistance per meter. So it'd be 1 over sigma times pi, and then it would be, really it would be a skin depth, so it would be 2 pi skin depth times A, plus the resistance of the outer one, 1 over sigma times 2 pi, same skin depth, but now it would be B, and you would have to add those together. And remember, this is gonna be resistance per meter I'm showing you. Y'all follow me on that? That's really it. These are standard, this is the kind of skin depth problems that Dr. Wentworth talks about, gives you in the book, and they're not hard to understand. He gives a picture of what I'm showing you, a cutout picture better than mine, on page 341, where he shows you the exact problem I'm trying to showcase. I'm going to mention one last thing, because I have to go through this, and explaining how material properties really impact engineering sometimes doesn't really have much impact until you start doing problems and you see how things change and vary. And especially, one of the design things you get is this all the time. Suppose I want a transmission line that has to be designed so that it can have no more than a certain resistance per meter given, right? That would be one constraint. And dimensionally, they'll say that the outer dimension has a limit, so that sort of tells you a lot about the thickness out here too. And there'll be constraints on that in the frequency range, and the skin depth is a function of frequency. So you'll go through and you'll have to like manipulate 3 different variables in a program to find out what is the best design. But you're not going to see this until I give you a problem like that. You can all probably appreciate in your mind, if you've got 3 equations or 2 equations with 3 or 4 unknowns, you adjust the variables until you get the result you look for. Let me mention one last thing. Final thing that we talk about that's so important is going to be power flow. Now you're used to power being voltage times current for instantaneous power, or really it's 1/2 V times I conjugate for complex power, when you're talking about the real part of complex power. And you've had this in grosses. This is macroscopic and it makes sense, but it's always voltage current, right, multiplied. When you talk about power flow, electromagnetic power flow, and you want something in watts per meter squared, the symbol we use is PAV usually, but I'm going to do it this way. This will be the instantaneous form of the power, and that's simply the E field as a function of time and space crossed into the H field as a function of time and space at a given point. And the units of this will be watts per meter squared. Now if you look at this, the E field's units are volts per meter. The H field's units are amps per meter. So volt amps would be watts. And then you have per meter, meter squared. So the units make sense. Everything makes sense about this. This is power flow. And when you do this, what we usually talk about is the average power flow. This one you write down. Average power flow is 1/2 the real part of the E field crossed into the H field conjugated. And these are phasor terms. Now, I'm going to go through this next time. I'm just trying to get you, I'm trying to set you up for this. If you look at this, this will come down to 1/2, and then it's going to be the magnitude, I'll prove this next time, of the E field squared over the magnitude of the intrinsic impedance of the media times e to the minus 2 alpha z, and there will be also the cosine of the phase angle associated with eta, and this will be propagating in the A Z direction. Now this is power flow. The units would be watts per meter squared. There's a reason I'm doing it now to give you a taste of it, because on Wednesday's class I want to make sure that I can start and discuss this in a way that will make sense to you. This is the general form of power flow in a material at a constant frequency, and I'll pick it up there. And I'll take your questions after class, if you've got it. All right. Did you guys get a test back today? We're sparse and tired.
Definitely tired.
Okay, it's just